Hi everyone, welcome back to my channel. In this video, I am going to solve Surface Chemistry CSIR NET previous year questions from 2017 and 2011 and 2016 video links I have mentioned in description. Please go through that. Now let's move to the question. Question 1. This is asked in CSIR NET June 2017. Consider aqueous solutions of two compounds A and B of identical concentrations. The surface tension of the solution of A is smaller than that of pure water, while for B it is greater than that of pure water under identical conditions. From this, one infers that four options given. Option A, surface concentration of A is smaller than its bulk concentration, and option B, surface concentration of B is larger than its bulk concentration, and option C is surface concentration of A is larger than that of B, and option D is surface concentration of A is smaller than that of B. Now let's see the solution. The key concept is the Gibbs adsorption equation. Here the equation gamma is equal to minus 1 by RT into d lambda divided by d ln c, where gamma is equal to surface excess concentration, that means difference between surface and bulk concentration, and lambda is surface tension. Now we'll see for compound A, surface tension is lower than pure water. Substances that lower surface tension are surface active and accumulate at the surface. Therefore, gamma A greater than 0. That meaning surface concentration of A greater than bulk concentration of A. Now we'll see for compound B, surface tension is higher than pure water. Such substances are negatively adsorbed and are depleted from the surface. Therefore, gamma B less than 0. That means surface concentration of B less than bulk concentration of B. So, since A and B have the same bulk concentration, surface concentration of A greater than bulk concentration greater than surface concentration of B. Hence, surface concentration of A is larger than that of B. So, here the correct option is option C. Surface concentration of A is larger than that of B. Now, let's move to the second question. Question number 2. This has asked in CSIR NET June 2017. An intense purple color Plasmon Band is exhibited by a colloid consisting of spherical. Here four options given. A is silver particles of 10 mm diameter, and option B is silicon particles of 5 mm diameter, and option C is gold particles of 5 nanometer diameter, and option D is iron particle of 3 mm diameter. Now let's see the solution. The solution is the intense purple color Plasmon Band is characteristic of gold nanoparticles. This phenomenon is due to surface plasmon resonance (SPR), where conduction electrons on the surface of metal nanoparticles oscillate collectively when exposed to light. So, gold nanoparticles, especially spherical particles of a few nanometers, show a strong plasmon adsorption band in the visible region, producing colors ranging from ruby red to purple or blue depending on particle size and shape. So, larger particles or other materials generally do not show this characteristic intense purple color. Now, evaluating the options. In A, they have told silver particles of 10 mm diameter. That is wrong because 10 mm is a macroscopic size, not the colloidal plasmon effect. So, there is no colloidal plasmon effect. In option B, they have mentioned silicon particle of 5 millimeter nanometer. This is not a typical plasmonic metal nanoparticle, so option B also wrong. In option C, they have given gold particles of 5 nanometer diameter. Gold nanoparticles of this size exhibit surface plasmon resonance and can give intense colors. So option C is the correct answer. Now, option D, iron particle of 3 millimeter diameter. This is also wrong because that is not responsible for a plasmon band in the visible region. Therefore, the correct answer is option C, gold particles of 5 nanometer diameter. Now let's move to the third question. This has asked in CSIR NET June 2017. The figure below depicts an adsorption isotherm of O2 on charcoal at 90 K. In the graph given V versus volume versus pressure. So at a pressure 25 torr, only 10% of charcoal sites are occupied by O2. Therefore, the ratio of adsorption to desorption rate constants in per torr is close to 4 options given 0.003, 0.004, 0.006 and 0.015. Now let's see the solution. We'll solve it by step. We'll solve it in step-by-step method. In step 1, set up the Langmuir adsorption model. For adsorption on a surface with fraction of sites occupied that is equal to theta and fraction empty that is equal to 1 minus theta. So, rate of adsorption is equal to Ka into P into 1 minus theta. Molecules land on empty sites proportional to pressure. So rate of desorption is equal to K into D into theta, Kd into theta. So molecules leave occupied sites. Now we'll see the second step. Apply the equilibrium condition. At equilibrium, rate of adsorption is equal to rate of desorption. Kap that into 1 minus theta is equal to Kd theta. Rearranging to find the ratio we want. Ka divided by Kd is equal to theta divided by P into 1 minus theta, that is equal to K. This is the Langmuir constant with units of pressure per unit. This consisted with the question asking for the ratio in per torr. So now we'll see the step 3. Plug in the given values. Given pressure P is equal to 25 torr, theta is equal to 0.10. That means 10% sites occupied. So Ka divided by Kd is equal to substitute values. 0.10 divided by 25 into 1 minus 0.10, that equal to 0.10 divided by 25 into 0.90, that is equal to 0.10 divided by 22.5. In step 4, you compute this. So Ka divided by Kd is equal to 0.10 divided by 22.5, that is equal to 0.00444 per torr, that is equal to 0.004 per torr. So step 5, match two options. This rounds to 0.004 per torr, that is option B. So option B is the correct answer for this. Here we'll see why the graph matters. Here the graph confirms this is a Langmuir type isotherm. That means V rises steeply at low pressure, then plateaus towards a saturation value that is approximately 200 cm3 per gram at high pressure. This shape is exactly what the Langmuir equation predicts, justifying use of theta is equal to Kp divided by 1 plus Kp. So equivalent form of the same equation for this problem. I hope you understood this question. Now we'll see the fourth question. This has asked in CSIR NET December 2017. The stability of lyophobic colloids is a consequence of the four options given. Option A, electrical double layer at the surface of the particle, and option B is van der Waals force between the particles, and option C is small particle size, and option D is shape of the particles. Now let's see the solution. The stability of lyophobic colloids is mainly due to the electrical double layer present around the colloidal particles. The lyophobic colloids, example gold sol or N6 sulfide sol, are inherently unstable because the particles have little affinity for the dispersion medium. So, their stability arises because colloidal particles acquire an electric charge on their surface, attracting counter ions and forming an electrical double layer. This creates electrostatic repulsion between particles, preventing them from coming together and coagulating. So, we'll check the options. In option B, they have given van der Waals force. It causes attraction between particles and promotes coagulation. That is wrong. And option C, small particle size, that helps in maintaining colloidal nature but is not the main stabilizing factor. And in option D, shape of particles, that does not determine stability. Therefore, the correct answer is electrical double layer at the surface of the particle. So for option 4, for this question, option A is the correct answer. Now, I think you understood this concept. In next video, I will come with some more previous year questions. If you like this video, please like, share and subscribe to my channel. Thank you. Have a good day.